Welcome to this deep dive. Today we are looking at this really just a massive $1 trillion bet that is, well, it's quietly rewiring the physical world right around you.
It really is.
You know, for decades, when you pictured a data center, you probably imagined something pretty static, just these endless, freezing cold rows of metal racks, right?
Yeah, the typical server farm.
Exactly. Just quietly storing your emails, your photos, your company spreadsheets. I mean, it was basically a giant static filing cabinet for the internet.
Right. Highly functional, but not exactly dynamic.
Right. But looking at the numbers and the presentations coming out of NVIDIA's massive 2025 GTC events, both in San Jose and Washington, D.C., plus a whole stack of industry white papers we've been going through, that old image is just completely dead.
It's a total relic at this point.
Yeah. We are talking about a fundamental shift in how the world computes. So today, we are unpacking what they call the AI factory doctrine. We're going to map out exactly how these mind-bending technological leaps are going to impact, everything from how doctors treat your health to how we predict the weather, all the way to space exploration.
It touches literally every sector.
It really does. So, okay, let's unpack this because we are not just doing a dry tech spec review today. We're looking at a roadmap to your future.
And what's fascinating here is that we are witnessing the physical construction of a completely new paradigm. I mean, the financial stakes are staggering.
Trillions, right?
Yeah. Industry projections show total data center capital expenditure hitting $1 trillion or more by 2028.
Which is just an unfathomable amount of money.
It is. And that capital isn't going toward building more of those static filing cabinets you mentioned. It is funding a wholesale transition away from traditional data storage into this completely new era of specialized, high-throughput intelligence factories.
Intelligence factories.
Right. We are moving from facilities that just store what we've already created to factories that generate new intelligence entirely on demand.
Okay, so to really grasp this AI revolution, I think you first have to understand the staggering scale of the physical hardware being built to support it.
Absolutely. The foundation is physical.
Right, like if the old data center was that static filing cabinet, the new AI factory is a dynamic, liquid-cooled, high-speed assembly line for human thought. And the engine driving that assembly line is this shift from NVIDIA's older HGX systems to their new Blackwell architecture.
Yeah, and the transition to Blackwell is fundamentally a story about eliminating bottlenecks.
How so?
Well, in the older HGX systems, you had multiple GPUs grouped together, and they communicated internally in these sort of small clusters.
Okay.
But Blackwell introduces a totally disaggregated design.
Yeah.
The NVLink switch, which is basically the vital communication bridge routing data between all these chips, it's been completely extracted and centralized.
Wait, if you centralize the communication switch, aren't you just moving the bottleneck to the center? I mean, how are they avoiding a massive traffic jam when every single chip tries to talk at the exact same time?
Oh, well, that's the genius of it.
Yeah.
They avoided it by engineering a communication highway with just unimaginable capacity.
Okay.
Centralizing the switch actually means every single GPU in a massive rack can now communicate with every other GPU at full bandwidth simultaneously.
Wow, so no waiting in line.
Exactly. You aren't routing data through this multi-step maze of connections anymore. It is a direct, dedicated lane for every single chip. But, achieving that requires pushing manufacturing to its absolute physical limits.
Right, because of the density.
Right. We are talking about a single computing rack going from roughly 60,000 components in previous generations to 600,000 components per rack with Blackwell.
That is insane. 10 times the physical complexity squeezed into the exact same footprint. And because of that extreme density, they had to fundamentally change the laws of thermodynamics for these systems, right? Like, they are officially replacing air cooling with liquid cooling.
They had no choice, honestly.
Because a single Blackwell rack consumes 120 kilowatts of power. And just to put that in perspective for you listening, that is enough electricity to run an entire neighborhood of houses.
Yeah, dozens of homes.
All concentrated into a space roughly the size of a large refrigerator.
Which perfectly explains the underlying mechanism of this whole design. I mean, why liquid cooling? Why this massive rack-scale architecture? It is entirely about increasing compute density.
Right.
AI models now demand trillions of calculations per second, and air cooling just relies on fans pushing air molecules across a heat sink.
Which works fine for a normal computer.
Sure, but at 120 kilowatts, you would need literal hurricane-force winds to pull that heat away.
Just blowing through the server room.
Which is physically impossible in a data center. So liquid is significantly denser than air. It absorbs and carries away heat at a magnitude that allows you to compress all that computing power without literally melting the silicon.
Right, without it just turning into slag.
Exactly. And that density gives you a memory bandwidth of 570 terabytes per second. And ultimately, it delivers 1 exaflop of computation per rack.
1 exaflop. I mean, to put that number in perspective, back in 2012, there was a supercomputer called Titan, and it was the fastest in the world. It took up a massive warehouse-sized room.
Right, massive facility.
And today, 1 exaflop means we are cramming that entire warehouse of supercomputing power into a single server rack.
It's breathtaking pace.
It is, but they aren't just building these building-sized factories either. They also shrinking this down for the individual. I was looking at the technical blogs, and they highlight the new DGX Spark and the DGX station.
Oh yeah, this is where the AI factory reaches the desktop. They are packing 20 petaflop PS of AI computation and 72 CPU cores into an AI-powered PC.
On a desk.
Right on a desk.
Yeah.
So a researcher, an engineer, or a data scientist can have what used to be considered national laboratory class supercomputer performance sitting right next to their coffee mug.
Just plugged into a standard wall outlet.
Exactly.
It's incredible. But I actually have to push back here for a second.
Okay, sure.
We're talking about all this new hardware and this trillion-dollar spend. But the data also shows the new Blackwell GB300 NVL72 system is, what, 4.2 times faster than the previous Hopper generation.
Yep, that's accurate.
Okay, so if the chips are over 4 times faster, shouldn't we theoretically need less hardware to do the exact same job? I mean, why the trillion-dollar price tag if everything is suddenly so much more efficient?
That's a great question. And if we connect this to the bigger picture, the answer really lies in how the software itself is evolving.
Okay.
We are moving away from simple perception and generation, like asking a chatbot to summarize an email or write a quick poem, to what is called agentic AI.
Agentic AI.
Right. The industry is shifting from software as a service to service as software.
Meaning what, exactly?
Meaning enterprise operations are anticipating an incoming workforce of 10 billion digital AI agents.
10 billion?
10 billion. And these agents don't just predict the next word in a sentence. They require a massive amount of inference compute to actually reason through complex problems step by step.
Oh, I see.
Yeah, this is driven by a mechanism called test time scaling, or as it's more commonly known in the industry, long thinking.
Long thinking. Okay, so instead of the AI just spitting out the first answer that comes to its digital mind, it actually pauses and thinks.
Exactly.
So for you, the listener, this means the AI tools you use at work are about to stop giving you instant kind of generic drafts and start taking maybe 5 minutes to return a perfectly reasoned, highly complex final product.
Right, because it's generating thousands of unseen thinking tokens behind the scenes. It's exploring decision trees, it's debating with itself, finding flaws in its own logic before it finally answers you.
And that operational shift, that long thinking, creates the economic formula justifying the trillion-dollar hardware spend.
Precisely.
Because test time scaling means models will drive 100 times the token generation compared to older models. And in the AI economy, computing 100 times the tokens equals 100 times revenue opportunity for the operators of these AI factories.
You got it. It transforms inference from a basic operational cost center into a highly profitable, high-throughput utility service.
Wow. But running a factory that complex has to require a totally new operating system, right? You can't just run an army of 10 billion agents on traditional enterprise virtualization software like VMware.
No, absolutely not. It would crash immediately. That's why NVIDIA introduced Dynamo.
Dynamo?
Yeah, it's an open-source inference software system designed specifically to act as the OS for these new factories.
But how is it different?
Well, if traditional software is like a rigid train schedule, very fixed, predictable paths, Dynamo is like a highly advanced air traffic controller.
Oh.
It dynamically reroutes massive data workloads to open GPUs based on real-time demand, ensuring none of those 600,000 components we talked about are ever just sitting idle.
So it manages the chaos perfectly.
It does. But the true competitive advantage, the real moat here, is the broader software platform beneath it. At GTC, CEO Jensen Huang actually highlighted the CUDA-X libraries as his favorite slide.
Really? His favorite slide was a software library.
Yeah, because these software libraries are the foundation powering incredibly niche, highly complex scientific workloads. Take computational lithography for chip manufacturing, for instance.
Right, which sounds like incredibly dense jargon, but it's actually fascinating when you dig into it.
It really is.
Computational lithography is basically using AI math to bend light. Manufacturers use it to calculate the exact interference patterns of light required to print transistors on silicon that are, and this blows my mind, actually smaller than the wavelength of the light being used to print them.
It's literally mind-bending physics enabled by software.
Yes. But making that software accessible to the wider enterprise market, that has to be the next hurdle, because businesses want to utilize this new workforce of digital agents, but they face massive friction regarding security, governance, and just basic integration.
Yeah, the barrier to entry can be really high. That is why we are seeing the rollout of NIM's NVIDIA inference microservices alongside things called AI blueprints.
Okay, what do those do?
They are standardized, pre-optimized software building blocks. So a company doesn't have to build the complex underlying AI architecture from scratch, which takes years and a ton of money.
Right.
They simply assemble these secure blocks to deploy teams of AI agents safely and efficiently.
Okay, so we've explored how this incredibly dense, liquid-cooled intelligence works inside the data center. But intelligence isn't meant to just sit in a server rack, right? It eventually needs to interact with our world.
Exactly, it needs a body.
Yes. And here's where it gets really interesting. Because the transition from digital intelligence to physical AI and robotics is being valued by analysts as a $50 trillion opportunity.
50 trillion. It's almost hard to wrap your head around. That figure represents the complete reindustrialization of global economies.
Wow.
But bridging the gap between a digital brain and a physical robot is incredibly difficult. You don't just...
Right, because you don't just build a $1 million robot and hope it works on a busy factory floor.
Exactly.
You build a digital twin. Think of it like a Broadway dress rehearsal, but for heavy industry. You build a perfect virtual replica of your factory in NVIDIA Omniverse.
Yeah.
And you run the simulation, you let the virtual robots make all the mistakes, right? They drop the virtual parts, they crash into the virtual walls. You figure out the entire workflow in a space where failure costs absolutely nothing, long before you ever pour concrete in the real world.
And major industrial players are leaning heavily into this. Siemens, TSMC, and Foxconn, they're building these factory-scale digital twins right now.
And BMW is doing something really wild with it, too.
Oh, BMW is taking it a step further. They're actually using human-piloted avatars to fly around inside the digital twins of their battery assembly factories.
Like a video game.
Very much like a video game. They observe and optimize the robotic workflows in real time before the physical factory even goes online. But, for those virtual dress rehearsals to actually translate to the real world, the simulation requires a flawless understanding of physics.
Because the virtual world has to perfectly mimic gravity, friction, material resistance, everything.
Right, otherwise the training is useless.
Exactly. And that's where the Newton open source physics engine comes in, which was built in collaboration with DeepMind and Disney.
Yeah, and Newton goes far beyond basic collision detection. It calculates physical dynamics at a granular level so the AI can learn mathematical reality.
Give me an example of that.
Well, for example, it features specific solvers for cloth. So to teach a robot to fold laundry, the engine calculates the tension, shear, and folding resistance at thousands of micronodes across a digital piece of fabric.
Oh, wow. So it's not just a visual simulation.
Exactly. It's feeling the math of the fabric. It even has solvers for granular materials like sand or soil, calculating thousands of individual particle interactions. So a autonomous excavator can learn exactly how much torque is required to dig through wet dirt versus dry sand.
And they take that incredibly accurate physics engine and use it for something called Isaac GR0T Dreams.
Yes, the dreaming capability.
Using the Cosmos Foundation models, the system generates synthetic training data for robots basically through dreaming. It can do passive dreaming, where you give it a single 2D image and a text prompt, and it hallucinates endless video scenarios of a robot completing tasks in that specific environment.
It's remarkable. And it also enables lucid dreaming.
Lucid dreaming?
Yeah, developers can teleoperate virtual robots inside these AI-generated physics-accurate worlds in real time. They can introduce edge cases like unexpected obstacles or sudden changes in lighting just to test the robot's reaction.
So they're throwing curveballs at it in the dream.
Exactly. It allows autonomous systems to train on millions of hours of operational data without a physical robot ever taking a step.
It's essentially the Matrix, but built specifically for robots to learn. And this simulation-first approach is the exact same mechanism bleeding into autonomous vehicles, isn't it?
It is 100%.
We saw massive partnerships announced with General Motors and Uber. Uber is targeting 100,000 autonomous vehicles on the road by 2027 using the Drive AGX Hyperion 10 reference architecture.
But scaling autonomous vehicles to that volume hinges entirely on safety verification.
Right, you can't just put 100,000 unverified robots on city streets.
Exactly. This is why the Halo safety framework was introduced alongside the hardware. You see, AI can often act as a black box, making decisions that are hard for humans to audit.
Right, we don't always know why it did what it did.
Right. So the Halos framework involves reviewing every single one of the 7 million lines of code in the autonomous system. It basically puts a transparent wrapper around the AI, and it mandates third-party validation to ensure every decision the car makes is deterministic and completely explainable to regulators.
Which is exactly the level of scrutiny you want before 100,000 robotaxis are deployed in your city.
Exactly.
The simulation-first approach, combined with frameworks like Halos, closes what engineers call the sim-to-real gap. It makes the business case viable because the safety is mathematically validated before the rubber ever meets the actual road.
It de-risks the whole enterprise.
Yeah. So we've got AI driving cars and orchestrating battery factories. But how does this gigawatt-scale intelligence actually reach the edges of the world? Like, how does a massive exascale supercomputer in a data center actually help a community health worker in a rural clinic?
It is a critical question of deployment. And the relationship between the massive data center and the rural clinic is really all about where the heavy lifting occurs.
Okay, lay that out for me.
The gigawatt AI factory handles the incredibly energy-intensive process of training the models, right? It's churning through petabytes of raw data.
Doing all the hard math.
Right. But once that intelligence is formed, once the model is trained, it can be distilled, optimized, and deployed onto tiny, low-power edge devices operating out in the real world.
Okay. A perfect example of this in the research is the Cephala microscope.
Yes, brilliant project.
Manu Prakash at Stanford is using a tiny computing module called the Jetson Nano to power a low-cost, self-driving microscope. Because the heavy training on what disease looks like was already done back in the factory, this little edge device can analyze red blood cells in real time.
In the field.
Yeah, scanning 3 million cells a minute to detect malaria in rural clinics, all without needing a massive internet connection.
It's amazing. It demonstrates how edge AI can radically democratize global public health. And, moving into centralized healthcare, J&J MedTech is utilizing the Omniverse platform and Cosmos models to simulate the Monarch robotic-assisted urology platform for treating kidney stones.
Okay, so surgical robotics.
Yes. Endocrinologists historically suffer high rates of orthopedic injury from long, highly repetitive procedures.
Just from standing there operating the tools.
Exactly. So by building a digital twin of the human anatomy, the operating room, and the robotic instrument all together, they can mathematically optimize the ergonomics of the procedure.
Wow, literally solving surgeon fatigue with a digital twin.
Right. Furthermore, NVIDIA's Clara open models like Codon-FM and LabProteina are mapping RNA and generating 3D protein structures atom by atom, which massively accelerates drug discovery.
So it's mapping the human body, but the exact same architecture is being used to map the entire planet. The sources highlight the Earth-2 platform, which utilizes a foundation model called SeqBottle and a framework called Physics Nemo.
Yeah, for climate and weather.
Right. The IMI-RE Corporation used this AI to take sparse data from just 50 weather stations in Oklahoma, just 50 data points. And they modeled the winds and precipitation for the entire state at extreme high resolution in just 1 hour running on a single GPU.
Which relies on a mechanism called score-based data assimilation.
How does that work compared to old weather models?
Well, traditional weather forecasting would take millions of CPU hours on a supercomputer to simulate every molecule of air in a grid. It's incredibly slow.
Right.
Instead, the AI has already learned the underlying physics of the atmosphere. It takes those 50 sparse data points and accurately generates the missing pieces between them almost instantly.
So it's filling in the blanks.
Exactly. This allows disaster preparedness agencies to run localized simulations of extreme weather events in seconds, fundamentally changing climate risk assessment.
It's incredible. So from the cellular level to the atmosphere, all the way to the vacuum of space.
Oh yeah, the lunar mining project.
Yeah. SoftServe is applying Omniverse to simulate autonomous fleets of drones, excavators, and haulers with a mission to mine ice on the moon. They use real-time visual mapping so drones can explore lunar caves in a physics-accurate simulation, dealing with lunar gravity and regolith friction, all while sitting safely on Earth.
And this widespread applicability is exactly why governments worldwide are now treating this level of compute power as critical infrastructure.
Meaning they see it as a national asset.
Exactly. They're realizing that relying on external systems is a huge vulnerability. So the trend of sovereign AI is rapidly accelerating.
Right. We should mention the sources focus on the UK government as a prime example here, building the Isambard AI supercomputer with over 5,000 chips as part of their AI Opportunities Action Plan.
Yeah, and the idea of sovereign AI is simply about a nation utilizing its own domestic infrastructure to train models that reflect its own population, culture, and security needs.
Right, treating compute power like the electrical grid or the water supply, just a fundamental utility for the 21st century.
Exactly.
But if compute is a utility, the demand is going to scale infinitely. How does the hardware roadmap possibly keep up with that? NVIDIA announced this new annual rhythm for hardware releases, right? Which is basically forcing the entire industry to move at light speed.
It is a relentless pace.
We start with Blackwell Ultra in the second half of 2025. But the real foundational leap is the Vera Rubin architecture coming in late 2026.
Yeah, the Rubin chips are moving to a 3-nanometer manufacturing process,
Right.
but more importantly, they are transitioning to HBM4 memory.
Why is that memory shift so critical?
Well, earlier we discussed how long thinking leads to a massive explosion in token generation.
Yeah, the 100x increase.
Right. If a chip is generating that much data, memory bandwidth becomes the ultimate bottleneck. The processor literally starves for data because it can't move it fast enough.
It's thinking faster than it can write it down.
Exactly. HBM4 memory widens that pipeline significantly. The Vera Rubin GPU is targeting 50 petaflops of FP4 performance.
An FP4 meaning 4-bit floating point, so they are actually using lower precision math because an AI doesn't always need 64-bit precision to figure out the next logical step, right? It just needs massive volume and speed.
Exactly. It's about efficiency.
And then Rubin Ultra in 2027 doubles that to 100 petaflops, followed by the Feynman architecture in 2028. But I have to wonder, as you pack more and more of these hotter, faster chips into a data center, how do they physically send data to each other across a massive building without lagging?
That challenge is driving the massive networking push highlighted in the roadmap, specifically Spectrum-X and photonics.
Photonics, so using light.
Yes. Rather than pushing electrical signals through copper cables, which generates heat and suffers from signal degradation over long distances, photonics uses actual light transmitted over fiber optics to connect millions of GPUs.
That's
It
wild.
vastly reduces energy consumption while maintaining perfect signal integrity across these gigawatt facilities.
Using light is incredible, but even photonics feels like, I don't know, stepping stones when you look at the ultimate frontier they discussed, quantum computing.
The holy grail of compute.
They announced the new NVQLink interconnect. And I feel like if upgrading traditional networking is like moving from a bicycle to a sports car, coupling GPUs with quantum processors using NVQLink is like learning how to teleport.
That's a good analogy.
Because it operates on a completely different paradigm of physics.
It does. NVQLink enables direct communication between traditional GPUs and quantum processors with a latency as low as 4 microseconds.
4 microseconds.
Barely perceptible. And to aggressively pursue this, a dedicated quantum research lab is opening in Boston, collaborating directly with MIT and Harvard. The Department of Energy is already partnering to integrate this technology into supercomputers like Solstice at Argonne National Lab.
Which will feature an astonishing 100,000 Blackwell GPUs working in tandem to drive exascale scientific discovery.
Right, and the Equinox system will have 10,000 GPUs.
100,000 GPUs in one system. It's almost difficult to wrap your head around the amount of data that we'll process.
And this raises an important question about how we govern and fuel all these future leaps in innovation.
Yeah.
At the DC conference, a major theme among researchers was the open source AI debate. The consensus presented by the panelists was that open models like the Llama, Nematron, and Cosmos families represent the fastest path to both innovation and societal trust.
Because everyone can see under the hood.
Exactly. Just as open source software like Linux became the invisible foundation of the internet era, these experts argue that transparent, open AI models allow universities, startups, and governments to collaborate globally.
Okay, that makes sense.
They argue that keeping the technology open, rather than locked behind corporate doors, makes it inherently safer and more accountable.
Okay, we have covered an incredible amount of ground today. Let's recap this journey really quickly. We started inside the $1 trillion liquid-cooled AI factories, breaking down how the long thinking of agentic AI is fundamentally altering the density and power of the hardware we need.
Right. The shift to services software.
We then followed that intelligence out into the physical world, exploring how hyper-accurate digital twins and physics engines are being used to train robots and autonomous vehicles before they are even built.
The simulation-first approach.
From optimizing how we treat kidney stones and detecting malaria with tiny edge devices, to simulating global weather patterns and, honestly, mining the moon. And finally, we looked over the horizon at a relentless annual roadmap that leads us through photonics and straight into the dawn of quantum integration.
It's a lot to take in, but I want to leave you with a final thought to mull over.
Oh, please do.
Early on, we discussed how enterprise operations are eagerly anticipating a new workforce of 10 billion digital AI agents. If the future of computing is services software, and every major industry now requires two factories, one to build the physical goods and one to compute the intelligence to run it, what happens to the very definition of a company?
Wow.
In the near future, a massive global corporation might not consist of thousands of employees. It might just be a handful of human directors managing a personalized, giga-scale factory of digital agents. So the question for you to explore is, what will your personal digital workforce look like?
Man, that is a profound thought. So what does this all mean? It means the future is already here, and that high-speed assembly line of human thought we talked about, it is powering up right now. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and we'll see you next time.